21 ECE 212T Control Systems Theory and Applications Unit 5 Controllability and Observability. In this video we are going to see controllability and observability of the control systems. The controllability determines if we can drive the system state to any desired value using an appropriate control input. It is essential for designing systems where precise control over the state is required. Observability indicates if we can fully determine the system state by observing its outputs over time. It is crucial for monitoring the state estimation in practical applications. These properties are fundamental for analyzing and designing efficient state space control systems. Both must be satisfied for a system to be well behaved in control and estimation tasks. Controllability of a system. A system is controllable if, starting from any initial state, it is possible to drive the state to any desired final state within a finite time by using an appropriate control input. Controllability can be mathematically represented by a controllability matrix. The controllability matrix is constructed as C is equal to B, AB, A square B, etc. A raised to n minus 1 into B. Here n is the number of states. The system is controllable if and only if the rank of the matrix C, that is controllability matrix, is equal to n. Here n is the number of state in the system. The controllability ensures that we can influence the system's states entirely through inputs, which is crucial for effective control design. Observability of a system. A system is observable if its states can be fully determined from the output measurements over a finite period of time. The mathematical representation for observability. The observability matrix O is constructed as C, CA, CA square, etc. CA n minus 1. The system is observable if the rank of observability matrix O is equal to n, where n is the number of states. Observability ensures we can infer the complete states of a system using output data, which is critical for effective monitoring and control. The importance of controllability and observability. In system design, it ensures the system can be effectively controlled and monitored for proper functionality. In the stability analysis, uncontrollable or unobservable states may cause instability, impacting system performance. Controller and observer design. These properties are the foundation for designing state feedback controllers and observer-based systems. Let's see a problem on controllability. A system is given as x dash is equal to ax plus bu, where a and b are a is equal to 0, 1, minus 2, minus 3. B is a matrix with 0 and 1. So we can calculate the controllability matrix based on these A and B matrices, and we can determine whether the system is controllable. So to calculate the controllability of the system, the controllability matrix C is given as B, AB, A square B, etc. A n minus 1 into B. Here the rank of matrix A is 2. So here we can construct the controllability matrix C is equal to B, AB. So here n is equal to 2. So n minus 1 will be 1. So we can construct the controllability matrix as B, AB. So by calculating the controllability matrix, we can get C is equal to 0, 1, 1, minus 3. The rank of the C matrix is 2, which is equal to the size of the matrix A, that is 2, and the number of states are also equal to 2. Now let's calculate the determinant of matrix C. And from the matrix C, we can calculate the determinant as -1, which is not equal to 0. Since we obtain the controllability matrix C as a non-singular matrix with rank 2, the system is completely controllable. Next, we are going to see a problem on observability. A system is given as x dash is equal to ax plus bu and y is equal to cx, where A and C are given as A is equal to matrix 0, 1, minus 2, minus 3 and C is equal to 1, 1, 0. So to find out whether the system is observable, we need to calculate the observability matrix. The observability matrix is given as C, CA, CA square, etc. CAN minus 1. Here n is 2, the number of states or the rank of A. So here we can write the observability matrix as matrix O as C and CA. So after calculating C and CA, we can get the observability matrix as O equal to 1, 0, 0, 1. The rank of O matrix is 2, and which again equal to the number of states and the size of matrix A. So here let's calculate the determinant of O, and if we calculate the determinant, it is equal to 1 into 1 minus 0, that is equal to 1, and which is not equal to 0. So we have obtained the observability matrix as a non-singular matrix with rank 2. So we can understand the system is completely observable. The controllability and observability in state space design. State feedback design. Controllability is an essential tool to design a state feedback controller that can drive the systems to desired states. Observer design. Observability is required to estimate system states from its output for effective monitoring. Duality principle. Controllability and observability are dual concepts, meaning many results for one apply to the other in reversed manner. Practical implications of controllability and observability. Uncontrollable systems. Certain states cannot be influenced by inputs, potentially resulting in poor system performance. Unobservable systems. Some states cannot be measured or estimated, leading to loss of critical information. System modification. To address these issues, redesign the systems A, B or C matrices to improve controllability and observability. Controllability and observability. In conclusion, the critical importance of these properties are essential for analyzing and designing effective control systems. We can verify these properties by using mathematical tests to check whether the system is controllable or observable. The system readiness can be ensured by observing the controllability and observability matrices have full rank, and we can confirm the system is ready for practical implementation. Thank you.